Hello, in this video I'm going to go through a moments question with friction. These are the sort of questions that people quite often find intimidating because there's a lot of choices you can make in terms of which equations you're going to set up, and sometimes people just find that paralyzing. It really doesn't matter which choices you make, but there are some that are going to be better than others that just make the question that little bit easier to answer. So we'll try and pick those apart as we're going to go through. Right, so what's our situation here? We've got a uniform rod PQ, length 2A, resting one end at P on rough horizontal ground, and a point T resting on a rough fixed prism of semicircular cross-section of radius A. Right, so that's just described a diagram, but it's told us that we've got friction here and here at P and T. The rod is in a vertical plane parallel to the prism's cross-section, right? So that's telling us that the rod isn't skewed off to the side. So it makes our geometry a lot easier because everything's in the same vertical plane. Also tells us that the coefficient of friction at both P and T is mu, so it's the same on both of them. Right, the rod is at the point of slipping when it's inclined at an angle of 30 degrees to the horizontal. Right, well, if it did slip, it's useful to think of how the rod would move because that will tell us the direction of our frictional forces. So if it was going to slip, P would head off this way as the bottom of the rod moves off to the left, and then the rod would also slip down that way. So our frictional forces as the rod slides down will have to oppose those two arrows. Now we want to get a good force diagram, and we're only concerned about the rod. The ground and the prism are only of interest for the effect that they have on the rod. So we want to draw a force diagram for the rod. So I'm going to draw that separately so it doesn't get too cluttered on this picture they've given us. So there's the uniform rod. We've got our point P. We can put, first of all, in the middle, right from the center, we've got weight. So I'm going to put mg, although it hasn't told us what the mass of the rod is. I'm going to go with a capital M. I can only assume this is going to cancel and it won't be in our final answer. Otherwise, they probably would have told us to use a particular letter. So that's in the middle. Where is our point T? We need to know really which side of the middle of the rod it's on. So looking at the geometry of this setup here, we've got this right angled triangle going from P to T and then O, the center of the circle. If that's 30 degrees, from P to O is going to have to be 2A, and then this is going to have to be root 3 of A. So that's going to be on the opposite side to P on the rod. So T is going to be, say, here. We're going to have a normal reaction force going up there, so I'll call that R subscript T for our reaction force at T, and then we're going to have friction coming out of T as well, which I'll call F subscript T. So that's done those. Now we just need to add the forces at point P. Again, we've got friction opposing the motion, so I'll call that F subscript P. And then we're going to have another normal reaction force, which is R subscript P. So that's our full force diagram on all of this. We've also got some point Q up here. It's a little bit awkward with this friction. It's coming out of T. So it's one where you might want to draw the arrow just slightly off to the side, just so you can see where it's coming from. But, I mean, that's fine. It's not really much of a big deal. Right, now this is where you've got to start making choices. But remember that just because we've got a rod going on here and we're bringing in moments, all we're doing is moving from just having resolve in 2 dimensions to now having resolve in 2 dimensions and take moments about points. It just gives us another equation or set of equations that we can construct. So let's start with resolving first, because that's what we're used to doing. So we could start with, well, even here you've got a choice. Do you want to resolve vertically and horizontally, or do you want to resolve perpendicular to the rod and parallel to the rod? Well, it doesn't actually matter which is why you need to be good at resolving forces. There's no obvious choice here. You know, when you might be looking at it thinking, well, if we got a lot pointing in a particular direction, which might make things a bit easier. And we have got 2 pointing up and down, 1 pointing to the side, but then we have got 1 perpendicular to the rod and 1 parallel to the rod. So it's, plus the angles are fine. We've got all of these 30 degrees kicking around all over the place. So I'm going to go for, because it doesn't really matter, so I'm going to go perpendicular to the rod, and I'm going to resolve that way. So let's add on a few angles just to remind ourselves on these. We've got 30 degrees there, so that's going to be 30 degrees there, and that's going to be 30 degrees there. So that should help. So we know the rod is in equilibrium, so all we've got to do is each direction is going to be equal to the other. So going up from the rod, we've got RT, and that's already perpendicular, plus RP cos 30, so root 3 over 2. So they're the ones going upwards, and then we've got 2 coming down. It's got to equal to mg cos 30. I'll fill that in as I'm going, root 3 over 2. And fp sine 30. So fp over 2. Right, so that's our perpendicular to the rod. So let's now do parallel to the rod. And we've got ft just on its own. So ft. We've got, what else we've got pointing in that direction? The RP is pointing in that direction. So we're going to have RP sine 30. So RP over 2. We've got the FP cos 30. FP root 3 over 2. And that has got to be equal to mg sine 30. mg over 2. Right, so we've set all those up. Now we also know, of course, that FP is equal to mu RP and that FT is equal to mu RT. So we can get rid of our FP and our FT, and that's reduced another thing out of all of these. So let's get rid of this term here and replace that with a mu RP over 2. And let's get rid of this term here and replace that with a, which one was that? That was mu RP root 3 over 2. And we can replace that one with a mu RT. So we've now got 2 variations on our resolving perpendicular and parallel. So now we've got to move on to doing moments, because looking at these equations, we can see we've got RT, RP, and mu in each one of them. Oh, and an M as well. So we've got far too many unknowns in all of this. So let's take some moments. Now we've got a choice. Yeah, you can take moments anywhere really. So we want to at least eliminate one unknown, preferably more. So the obvious picks are, well, do we go with P or do we go with T? So if we did moments about P, we're going to eliminate RP, FP, and FT won't count because it's just pointing directly away from P. So that looks quite nice. If we were going to do moments about T, then we get rid of RT and FT, but we're going to have both of RP and FP in the equation. So we're not eliminating quite as much. So it looks as though doing moment about P is going to be our best bet initially. So if we're doing moments about P, now remember we've got the distance of mg is a away. So that's going to be mg a cos 30, so root 3 over 2. That's going in the clockwise direction, and in the anti-clockwise direction, well, it's easier because that's already perpendicular, and we know that that is a root 3 away. So that is RT times root 3 and another a. I'll stick the a at the front so I don't think it's sitting under the square root. We can cancel some things here because the a root 3's are just going to cancel. So this is immediately giving us that RT is equal to mg over 2. So that is particularly useful because we can replace that in our original equations. Right, so let's take stock of what we've got here out of all of these and start replacing some RTs, and then hopefully we haven't got that many unknowns kicking around anymore. So going back to our first equation, I'm also going to multiply everything by 2 because you can see we've got these halves everywhere. So we'll have mg plus rp root 3 equals mg times root 3 plus mu times rp. Well, that's good because, okay, we've got these mg's, but we've only got rp's and mu's in there otherwise, so that's really cut things down. And then now let's look at our second one, which again we can multiply everything by 2 as we're going through. So we've got a mu RT, so a mu mg, and then RP over 2, which is just now RP, plus this thing, mu RP root 3, and that is equal to mg. Right, so if we can eliminate RP out of all of these, set them equal to each other, and then we can solve for mu, hoping that those mg's are just going to disappear. Right, so let's make RP, because we're not interested in that, the subject of each one of these equations. Right, so for the first one, what are we going to have all in all? So let's get the, so yeah, coming off of this top one, the mg's on the same side. So we're going to have an mg root 3 minus 1, and then we'll have an rp root 3 minus mu we're going to have to divide by. So root 3 minus mu. So that's one expression for RP. And from the second equation, we're going to have mg 1 minus mu. And then we're going to have to divide by 1 plus mu root 3. 1 plus mu root 3. So that's made RP the subject of each one, and then we've equated them. So wonderfully, we can then cancel our mg on each one of them, and now we just got to cross multiply these and turn it into a quadratic. So we've got root 3 minus mu root 3 plus mu squared is equal to root 3 minus 1 plus 3 mu minus mu root 3. Right, we've got lots of things that seem to be able to cancel here. So we can get rid of a root 3 on each side. We can get rid of a minus mu root 3 on each side, which leaves us with mu squared minus 4 mu plus 1 equals 0. So we've just got to solve this, and then we're sorted. So we can complete the square on that. I'm just going to have to sneak up here in order to fit it in as I've dropped off the page. So we're going to have a mu minus 2 squared. Then we're going to have to take 4 off and add 1. So that's going to be equal to 3. So mu is going to be equal to 2 plus or minus the square root of 3. Well, mu's got to be between 0 and 1, so we're going to have to take that root 3 off. So mu is going to be equal to 2 minus the square root of 3. Right, so that's dropped out quite nicely. There's some tricky algebra that we've had to work through on there. But it wouldn't have mattered. So you could have done all of this again, and you could have said, well, I'm going to resolve vertically and horizontally rather than perpendicularly and parallel. Wouldn't have made any difference. So don't get fixated on how you're doing that, providing you're resolving in two directions and they're perpendicular to each other. Then if your algebra is good enough, this is why being slick at your algebra is so important, because it solves a lot of problems when you're getting into complicated moments questions. It doesn't matter how you do your resolving, you'll be able to deal with it because your algebra is good enough. Then we got rid of moments. Now you could have taken moments somewhere else. Again, that probably would have been fine. If we'd taken moments about t, okay, we would have had an RP and an FP in it, but we can express FP in terms of RP. You've just got a slightly more complicated moments equation. It won't stop you from being able to answer it. The key thing is that you're taking a moment either around P or T, because then it's eliminating one of your unknowns, either the RT or the RP. But it doesn't matter which one you pick. Again, as long as your algebra is good enough, then it won't make any difference. It's probably quicker to have done it with a moment about P, but there's not really going to be that much of a difference. So this is a complicated question, but you're using the same tools every time when you're looking at something like this. As soon as you see that we've got an object that's got extended properties, this has got length, it's not just a point, then it just expands from just resolving forces, which is what we do with points, to doing resolving forces and doing moments if we've got an extended body. So you're applying the same method every single time. It's just a little bit heavier on the algebra.